Okay, welcome to Unit 2, which is all about velocity. This unit's going to be split into 3 videos. The first video, which is this video, is going to cover the introduction to velocity, along with the introduction to displacement and distance. The second video is going to be talking about graphical analysis, and then finally the third video will be talking about motion maps. So let's go ahead and get started with Unit 2. Like I said, Unit 2 is all about velocity. In order to demonstrate this, let's look at a simple lab that might be done if you were in an in-person class. What we have here is we have a buggy cart that is set to go at a constant speed, so no speeding up or no slowing down. Now what I do is I'm going to take the car and I'm going to align it on the walls. Okay, so let's say we set the car on the wall and we would call this spot right here the 0 mark. Or in other words, this would be our starting point. Then what I do is I measure on the wall every 5 meters. And every 5 meters, I'm going to put a mark. We have 5 meters, 10 meters. Right here we have 15 meters, 20 meters, and then finally 25 meters. Then what I do is I turn the car on, and as soon as the car starts going, I start my timer. So the timer would be initially at 0 seconds right here at the 0 mark. I'd let the car go, and as soon as the car passed the 5 meter mark, I would hit the time, but I would continue letting it go. As soon as it passed the 10 meter mark, I would record another time, 15, 20, and then finally I would stop the clock at 25 meters. Then what I do is I turn the car around. So let's go ahead and flip this from left to right. Now what the car is going to do is it's going to go backwards. This is going to be my trial 2. So I'm going to start the clock at 0 seconds, but this time it's starting at the 25 meter mark. Then the car goes back, passes the 20, the 15, the 10, the 5, and then finally gets back to 0 meters, in which case I stop the clock. This is a very simple lab that's going to demonstrate some very basic but important concepts about velocity. So if we were to look at the data, let's go ahead and look at this sample data that we might get. On the left column right here is the time in seconds. 0, 2, 4, 6, 8, and 10 seconds, and the corresponding distances that they were. So at the 0 meter mark, I was at 0 seconds because that's where I was starting. Once the car had passed the 5 meter mark, that was 2 seconds. The 10 meter mark took 4 seconds. 15 took 6, 20 took 8, and finally 25 meters took a total of 10 seconds. Then what I did is when I turned the car around, I produced these times. Notice what happened. It was at the 25 meter mark that the time was 0, because this is where I was starting. Then it took 2 seconds to get to the 20 meter mark, 4 seconds to get to the 15 meter mark, 6 seconds to get to the 10 meter mark, 8 seconds to get to 5, and finally 10 seconds to get back to the origin or the starting point, which was the 0 meters. Now what I'm going to do is I'm going to graph this data, and I'm going to first start by graphing the data that was going away. So what that means is, notice my graph here, I have distance or position on the y-axis, and on the x-axis I have my time. So going away, or the beginning, at 0 seconds, which would be right here, I was actually at the 0 meter mark. So I'm going to go ahead and put a dot right here at my origin. At 2 seconds, my data shows that at 2 seconds I was at the 5 meter mark. So I will put a dot there. At 4 seconds, I was at the 10 meter mark. At 6 seconds, I was at the 15 meter mark. At 8 seconds, I was at the 20 meter mark. And then finally at 10 seconds, I was at the 25 meter mark. We can now go ahead and figure out a relationship here, and the relationship is pretty straightforward. It's linear. So notice an object going at a constant velocity or a constant change in position over time creates a linear fit. Now let's go back and let's look at the returning trip for the car. So at time 0, be careful on this one, at time 0 or at 0 seconds, where was the car on the returning? You might be tempted to say it was at the 0 meter mark, but that's actually not true. At the 0-second mark, it was actually at the 25-meter mark that we had placed on the wall. So at 0 seconds, I would place a dot here at 25 meters. Then at 2 seconds, the car was at the 20-meter mark. At 4 seconds, it was at the 15-meter mark. 6 seconds was at the 10-meter mark. 8 seconds was at the 5-meter mark. And then finally, at 10 seconds, it had returned back to the 0-meter mark. Once again, this would create a linear fit. However, the difference here is that the linear fit has a negative slope. So let's look at some conclusions we've made here. The first conclusion we've made is that objects that go at a constant velocity are going to create a graphical fit that is linear. Notice, since the car was going at a constant velocity, it produced a linear line both away from the starting point and going towards the starting point, because the position or distance was changing at the exact same rate. However, when we go away from the origin or away from the starting point produces a positive slope, whereas going towards the origin or back towards the starting point produces a negative slope. So we see that the slope of the line on a position versus time graph also tells us the nature in which the object is moving according to the starting point, whether towards or away. Once again, these are some simple concepts but very fundamental and basic that are going to help us in the unit of velocity. So let's talk about some things that we've learned. First thing we've learned is that the slope of a position versus time graph is going to tell us the velocity. If we were to go back and look at the lines that we produced, let's go ahead and see what the slope would tell us. Let's focus on the blue dots, or the positive slope. If I were to ask you to determine what the slope was, we would use our slope formula, which is y2 minus y1 over x2 minus x1. A simpler way of writing that would be change in y over change in x. Now, what is the y? Well, the y is position, and position is measured in meters. So the top unit of our slope would be meters. What about change in x? Well, the x-axis is time. So when we think about change in x, we're really talking about change in time, which would be measured in seconds. So notice our slope would have the units of meters per second, and meters per second just so happens to be the units of velocity. So once again, the slope of a position versus time line is velocity. A simple saying helps us. As goes the slope, so goes the velocity. What that means is that as the slope becomes positive, we're going away from the origin, and as the slope is negative, we go towards the origin. Well, what about steepness and slope? For example, what if the slope wasn't this steep, but what if it was more shallow, like this? If the slope is shallow, like this, that means the object is moving slower. But if the slope is very steep, such as this, it's covering more distance in a less amount of time, meaning the object is going faster. So the slope and the steepness of the slope actually tells us also about the speed. And finally, we can mathematize this, or give it some math properties, by coming up with an equation here. And that is that the average velocity is calculated by taking delta x divided by delta t, or in other words, change in position over change in time. Please notice this is an average velocity. We're going to talk in just a moment about what the difference is between an average velocity and what we call an instantaneous velocity. Sometimes they're the same, but sometimes they are not. And we'll talk about the differences between them in just a moment. Now, we've been talking about these ideas of position and distance and displacement and kind of using them interchangeably. We've also been using the terms velocity and speed interchangeably as well. But what we're going to see now is that there's actually a difference between the two. There are two terms that you're going to need to be familiar with in this unit, and actually in physics as a whole. And those two terms are scalar versus vector. A scalar quantity is magnitude only. So for example, if I said I was driving down the street going 40 miles per hour, This is a magnitude. It's just telling me actual how much. 40 miles per hour is just telling me the actual quantity of speed that I have. However, a vector quantity is a magnitude plus direction. And that means it's identifying an origin and a direction from that origin. Typically, the origin going to the right and up is positive, but you have the ability to decide what you want to make positive. And we'll talk more about that later. So for example, a vector quantity would be if I said I was going 40 miles per hour east. In this case, not only have I established a magnitude, which is 40, but I've also told you direction, which is east. In physics, there are two common ways to indicate direction. The first way is using the north, south, east, west direction, and the other way that we'll see in just a moment is simply by using positive or negative signs. Now that we understand what scalar and vector is, let's go ahead and talk about our first scalar versus vector quantity. And that is the difference between displacement and distance. They might sound the same, but one of them is a scalar quantity, the other is a vector quantity. Can you guess which one's which? The scalar quantity is distance. Distance is defined as how much ground something has traveled. The vector quantity is displacement. And notice the difference in definition. Displacement is how far away from the origin something has moved. That might sound the same, but it's actually very different. Let's go ahead and look at the examples. All right, look at this first example right here. The question says, what is the total distance and what is the total displacement? Might seem like they might be the same thing, but they're not. Notice the pattern. It looks like an object is going up 2 meters, to the right 4 meters, down 2 meters, and to the left 4 meters. Let's first talk about what's the total distance. Well, you might be wondering, well, where does the object start? In this example, it really doesn't matter since the object is going in a circular or rectangular motion. But for argument's sake, we'll say the object started right here to the upper left. Remember, total distance is defined as the amount of ground that is covered. So let's look at this example right here. This object, whatever it is, went to the right 4 meters, went down 2 meters, so now we're at 6, went to the left 4 meters, so now we're at 10, and went up meter, which is now 12 meters. The amount of ground that was covered was 12 meters. However, displacement, remember, was defined as the distance, or excuse me, how far away from the origin something has moved. If we're establishing our origin at the top left with the blue dot, notice the object went right, down, left, and up, and ended up at the exact same spot that it started. So the total displacement for this object happens to be 0 meters. Now you might be wondering, well, what if we had made the origin down here? In this specific example, it doesn't make a difference because the object would still end up at the exact same place that it started. Let's go ahead and look at another example. Let's go ahead and take an example of this skier right here. Now, you'll notice that there are 4 images of the skier. A, B, C, and D. The A, B, C, and D are sequential spots in which case the skier is moving. So the skier starts at spot A, then in 1 minute gets to spot B, in 2 minutes gets to spot C, and then at time 3 minutes is at spot D. So the skier is moving in a back and forth motion. Same question, what is the distance and what is the displacement? The distance, remember, is the amount of ground covered by the skier. So let's take this bit by bit. First of all, the skier goes from spot A to spot B. Notice that this is 40 plus 100 plus 40, or in other words, 180 meters, simply by going from spot A to spot B. Then the skier goes from spot B to spot C, which is 100 plus 40, or 140 meters, simply by going from B to C. And finally, the skier goes from spot C to spot D, which is 100 meters. So if you add all of that up, the total distance, or amount of ground covered by the skier, ends up being 420 meters. Now, let's look simply at how much distance from the starting point. The starting point is right here at spot A, and the skier ends up at spot D. How far away is spot D from spot A? Well, 40 plus 100 is 140 meters. So the displacement was 140 meters. Let's look at one more example. This last example, it can be a little tricky. There's something different in this example that was not the same in the other two. And that is, the person who has made this problem has actually already given us a scale at the very bottom. In the problem before, you'll notice there was no scale, and so we assumed the origin was right here at spot A. However, in this example, the origin is established right here at spot 0. So notice the person which is starting the motion at spot A is actually starting away from the origin. That's going to become important when we talk about displacement. But first, let's talk about distance. Distance is defined as the amount of ground covered. So, the person goes from spot A to spot B, which if we look is 10, 20, 35 yards. Then goes from spot B to spot C, which ends up being 10, 20 yards. And finally goes from spot C over here to spot D. And that ends up being 10, 20, 30, 40 yards. So if we add all of that up, 40 plus 20 is 60, plus 35 is 95 yards covered by the person. Now remember, displacement is how far from the origin. Remember, the origin is right here, and the person ends up at spot D, which is right here. Notice that the person ends up being negative 5 yards, from the origin. So that's the displacement of the person. Remember, displacement is defined as the distance from the origin. And in this example, the origin was predefined for us right here based on this scale. Now that brings up a very important point. How can distance be negative? Remember, how can displacement be negative? Remember, back here, displacement was a vector quantity, and vectors define not only magnitude, but also direction, and direction can be negative. So when we look at this problem right here, the negative simply implies direction, and that means negative is to the left of the origin, whereas positive would be to the right. This concludes the video on the introduction to velocity and displacement and distance. The next video will talk about the graphical analysis of velocity.